Hi, I'm Blair Epting,
And I'm Justin Swenson.
and this is our project on RLC circuits.
So the way an RLC circuit works is it can be represented by this second order differential equation, where you take the inductance times the second derivative of charge and add that to the resistance times the first derivative of charge, and then you add it to the charge divided by the capacitance, and this should equal 0. And also the charge over the capacitance should equal your voltage over the capacitance, which is what we'll be measuring with the oscope to get the dampening ratio.
Okay, right here is the transient response of our RLC circuit. On this top pink line was our maximum value of the transient response. The pink line on the bottom is our minimum value of the transient response. And then we did the maximum value minus the minimum value so that we were able to get our delta value. And then delta times 0.368, which equals 1 over E, plus our minimum value was able to give us this blue line right here. And then using the number of peaks before we reached our blue line, which in this case is 2, we were able to get our N value. And then using T, which is 2 pi divided by omega, we were able to get the next formula which was used, which is gamma equals 1 divided by the number of peaks times the period. And then using gamma, we were able to find the quality factor, which is omega divided by 2 times gamma. And then from the quality factor, we were able to get zeta, which is 1 divided by 2 times the quality factor, which is the dampening coefficient.
So we initially start with this circuit where we have OP amp comparing the voltage in, which we had as a 1 volt square wave going from 0 to 1 volts, and it was also comparing the voltage from a 10 kilo ohm 10 turn trim pot, and now it's connected to the gate of a MOSFET transistor. The source of the transistor was connected to ground, and the drain was connected to a 10 ohm 2 watt power resistor, which was connected to 5.2 volts of DC. And this was all connected to the resistor, inductor, and capacitor in series. So this was in parallel to that. And then to get our measurements, we had the oscope set so that this was the positive and that was the ground, so that we could actively measure the voltage across the capacitor, and that is what we used in our measurements.
Okay, during our original circuit, we had a couple issues which we then fixed in our revised version of the circuit. The first issue is with the 10 kilo ohm 10 turn trim pot, where we kept having issues with it moving around. So we then replaced it with a 10 kilo ohm resistor and a 4.7 kilo ohm resistor, which we created as a voltage divider, which fed into the non-inverting input of the amplifier. And then our second issue was that we burned out 2 10 ohm 2 watt power resistors, which came out of the drain of the MOSFET transistor. And then we replaced it with a connection of resistors which equaled the same resistance, except the heat was transferred over 4 resistors instead of 1, thus making each resistor not get as hot.
Our first circuit had a 10 ohm resistor, a 0.1 Henry inductor, and a 0.1 microfarad capacitor. After each trial, R, L, and C were changed back to these values so that each trial only had one different component compared to this circuit. This way, we could easily see what each change did to the dampening coefficient by comparing the dampening coefficient of each trial back to this trial. On the oscope, we were using channel 1 to measure the function generator, which was feeding into the OP amp, and channel 2 was measuring the voltage across the capacitor, which was giving us the transient response of the RLC circuit. Our next circuit used the original resistor and capacitor, but the inductor was changed to a 0.047 Henry inductor. Just like the first screenshot, this screenshot has the oscope where channel 1 is measuring the function generator into the OP amp, and channel 2 is measuring the transient response of the RLC circuit by measuring the voltage across the capacitor.
In this circuit, we go back to our original 10 ohm resistor and 0.1 Henry inductor, but instead of the original 0.1 microfarad capacitor, we used a 47 picofarad capacitor, which gave us a much lower zeta value and thus had many more peaks.
Our last circuit had a 39 ohm resistor. but still had the 0.1 Henry inductor and 0.1 microfarad capacitor. Channel 1 of the oscilloscope was still measuring the function generator into the OP amp, and channel 2 was measuring the transient response of the RLC circuit.
To conclude, in our parent trial with our 10 ohm 100 millihenry 0.1 microfarad components, we found a quality factor of 2.537, our dampening ratio to be 0.1971, and then from there we changed one component each time. First, starting out with changing the inductor, we found our dampening ratio to decrease slightly. Then we changed our capacitor, which made our zeta value significantly decrease. And at the end, we increased our resistance, which caused our zeta value to slightly increase overall.
Furthermore, some of the problems we encountered during our experiment were finding other resistors, capacitors, and inductors to use after our first trial so that the resistance, capacitance, and inductance of the circuit was changed. But some of the ones we used when measuring the voltage of the capacitor, there's either little to no transient response at all. And with no transient response, we can't use the 1 over E method to get the dampening ratio. So it took us some time to find good values for the RLC to get a dampening ratio. Another problem we encountered was burning the power resistor, but we did fix that by using the 4 power resistors instead of just 1. One last problem we encountered was having to estimate with the cursors on the oscilloscope. Particularly, we're trying to find the minimum voltage of the capacitor, because we were using offset, and we had to kind of estimate where the middle of the transient response was, and therefore by having an estimate, it did throw off our calculations a little bit.